This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, your professor for this University of Texas at Austin course, and we're at lecture 57. On lithography, we're going to talk today about resolution enhancement technologies, part one of a two-part series on that topic. So, if we're going to talk about resolution enhancement, maybe the first thing we should do is define what we mean by resolution. Now, I think we all have a basic idea of what resolution means. It is the smallest feature we can print, the smallest feature we're able to print. The key to this definition, though, this obvious definition of what resolution means, is defining what we mean by able to print. In manufacturing, able means the ability to print consistently, meeting the specifications required for manufacturing. In other words, for meeting the needs of lithographic quality. If we can print something and look at it and it's small, but it doesn't meet the quality requirements to be able to manufacture with that feature, then it isn't resolved from the perspective of manufacturing. So we often think about the research definition of resolution, which means if we can print it once and take a picture of it and stick it in a paper, we say it's resolved. But in manufacturing, we have to be able to print it repeatedly with good control and meeting all of the lithographic quality requirements that we've discussed in the past. Now, defining the smallest feature that meets all lithographic quality criterion is a bit daunting. So as a proxy for lithographic quality, we often use depth of focus. What is depth of focus? Depth of focus is the range of focus over which the given feature that we're interested in remains in specification. That means it has all of the desired properties, like the right CD plus or minus a certain amount, the right sidewall angle. If we think about a resist feature shaped like a trapezoid, we can define the sidewall angle as some angle relative to the substrate. And then we might also have a spec on the thickness of the feature, which might be less than the thickness of the photoresist originally due to resist loss phenomena. So if our resist profile meets all of its specifications, and it meets them over a given range of exposure, that is, has a given exposure latitude, then we say this is the depth of focus, the range of focus that keeps our feature in spec over a range of exposure. Now, once we've defined depth of focus, we're ready to define resolution. And this is how resolution is generally defined in a manufacturing environment. The smallest feature of the given type we're interested in that can be printed at least a given minimum depth of focus. If you push the feature size smaller, maybe we can print it, but we can't print it with sufficient control. And we use depth of focus as our proxy for how well it is, how easy it is to control that feature in a manufacturing environment. So that's the definition of resolution that we generally use in manufacturing. But notice that in that definition we had for a given feature type. There are different resolutions for different feature types. And the two most important resolutions we think about are the smallest feature that we can print and the smallest pitch that we can print. So the pitch is the repeating distance for repeating patterns, and for example, if I have just lines and spaces, then the pitch is simply the line width plus the space width. The feature size is, of course, just the feature size, or the critical dimension, CD. It could be the critical dimension of the line or the critical dimension of the space. We could have more complex shapes than just lines and spaces. We could have an array of contact holes, for example. We could have more complicated shapes, but in any case we have dimensions of individual features, and we have the pitch, or the repeating distance for these features. We often talk about the smallest half pitch, which is simply the smallest pitch divided by 2. And that way the feature size and the half pitch are more comparable to each other. But these resolutions are distinct, and as we'll see in just a moment, what determines the smallest half pitch is not the same as what determines the smallest feature size that we can print. So pitch. What is the pitch resolution, the smallest pitch that we can print? Often we describe the pitch resolution, the smallest pitch, as scaled by lambda over NA. So we use the scaling constant K pitch. You might recall K1 lambda over NA. Excuse me. K1 lambda over NA is our normal way of describing the Rayleigh resolution criterion. And all feature sizes scale as the wavelength, lambda, and the objective lens numerical aperture, NA. K-pitch has a hard cutoff, 0.5. This is for two-beam imaging, and to get two diffracted orders through the lens, K-pitch cannot be less than 0.5. If it is, we only get one diffracted order through the lens and we don't get an image. So this is a very hard cutoff for pitch resolution. We just can't do better than that. But to get to that limit is quite hard. In fact, going down to K-pitch of about 0.7, we can do that with kind of conventional means. But going beyond 0.7 requires extensive resolution enhancement technologies, which is what we're going to talk about in this lecture and the next. This hard cutoff of 0.5, though, is something you can't push beyond unless you use something called double patterning, and we're going to talk about that in a subsequent lecture. We're going to ignore that possibility for now, though. The feature resolution, on the other hand, is a little bit different. Now, the resolution is equal to K1 lambda over NA. This is our scaling equation. K1 is the scaled feature resolution. But unlike the pitch resolution, there's no hard cutoff for an individual feature. We can make K1 smaller and smaller and smaller. And as we do, it gets harder and harder and harder to control the feature that we're trying to print. The feature resolution, then, is limited only by CD control. Now, you recall from a previous lecture that CD control is determined by two factors. One, the magnitude of the process errors that exist in our manufacturing process, and the process latitude, that is the response of our process to those errors. So if we can improve the process latitude, then we get better CD control and better resolution. Or if we can reduce the magnitude of the process errors, we can also get better CD control and therefore better resolution. And this is maybe a little strange to say if we can improve the temperature uniformity of our hot plate, we have better resolution. Or if we can reduce the sources of focus errors that exist in our process, we can live with a smaller depth of focus, and that enables better resolution. But that's the way it is. For feature size, there's no hard cutoff. It's a matter of how well we can control. As a result, the feature resolution is always at least equal to, but generally better than, the half-pitch resolution. And to say that I can resolve 20 nanometer features, maybe you can, but that doesn't mean you can resolve 20 nanometer half-pitch. Maybe you can only resolve a 40 nanometer half-pitch, but 20 nanometer features. So you've got to be very careful which resolution you're talking about when you refer to resolution. Is it the minimum feature or the minimum half-pitch? They can be very different. So, given this definition of resolution, now we can ask ourselves, what can we do to improve resolution? And there are three main techniques that we used. First is something called optical proximity correction, or OPC. The next is off-axis illumination, or OAI. And the last one is phase shifting mask, or PSM. So as you can see, RETs love TLAs, three-letter acronyms. So we're going to talk about all of these in these two lectures on RET. Today, we're going to talk about OPC, optical proximity correction. We'll leave the other two to our next lecture. So OPC can also be thought of as mask shaping. We have a pattern that we want to print, say these two T patterns that are next to each other. This is what we want to print on the wafer. So in general, if we thought of lithography as a what you see is what you get imaging process, we would stick these shapes on the mask and we would be done. We would print the best we can. But in fact, what you see is not what you get when we're pushing our features near their resolution limit. So we need to modify the mask so that the printed result looks more like the design pattern. And going through an OPC process, we might get a mask pattern that looks like this. We go, wow, that doesn't hardly look anything like the original. And that's happening more and more. The final mask shapes that we use to print features can look a lot different than the features, the shapes that we actually want in the end result. The kinds of changes that we make are illustrated here. So suppose I have a line that's kind of an elbow-shaped feature, and then another line here with a couple of gaps in between or spaces in between. This is what I want to print on the wafer. To get the result that I want, I'm going to distort the mask to compensate for the distortions that happen in the imaging. So the first thing I'll do is add some serifs. For example, these little corner bulges on the line, and on this corner, an anti-serif where I take a little notch out of this corner here. These serifs help to make the corners less rounded than they otherwise would be. But also, these gaps might not print at the right feature size, so I'll move the edges a little bit, say this edge and this edge, compared to the design, so that when it prints at about the right feature size. And then finally, I might add a sub-resolution assist feature, SRAF, sub-resolution assist feature. These SRAFs, which are also illustrated as these features here, 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 and here, are too small to print. They're beyond the resolving capability. But their presence on the mask influences the printing of the nearby features, those features in proximity to that. So we're going to use these small features to influence the way the nearby things might be printing. And so those are called sub-resolution assist features. And we're going to put all of these kinds of changes in our mask in place in order to get features to print the way we want them. So you see these kinds of serifs here and here. Here's an anti-serif. You can see a cutout of the line here and here, sub-resolution assist features, and modifications of the edge positions here and here, all of which help to get a feature that prints closer to its ideal shape. What is the cause of this non-ideal imaging? The fact that we don't get a shape printed on the wafer that looks like what we want it to? Well, it's simply the diffraction limit. The fact that we're only capturing a small portion of the diffraction pattern, and therefore we're not capturing all the information as to where the edges should be. A very simple way to see that is with the images that result from an isolated feature compared to a dense feature. Here I have a pattern of lines and spaces. In the red, I have the image of an isolated line. So the line pattern is in the middle, and it gets dark underneath the line pattern and then is bright out here to either side. This is an isolated line in the red. But in the blue, I have a dense pattern of repeating lines and spaces. What I find is that the line, nominally on the mask, they're the same width, but when we look at the images, you see that the isolated line is wider. Right? If I think about the width as how wide this dark region is at some, say, intensity threshold value, I see that the red isolated line is wider than the blue dense line, and when I print this in photoresist, that's how it's going to print. The isolated line will be wider than the dense line. This is not some error in the behavior of the lens or of the photoresist or anything else. This is simply the nature of printing in the presence of low-pass filters in our lens. We're losing diffraction information, and that information about where the edges should print are systematically different for a dense feature versus an isolated feature. This proximity effect, in this case, is called the isodense bias, the difference between an isolated line and a dense line. In fact, though, the printed feature size will vary as a function of pitch. So I can imagine having a mask pattern like this with a certain CD, and then I vary the pitch, the distance, center-to-center spacing between lines of the same feature size. If I then print these patterns and measure their resist feature size, CD, as a function of the pitch, we will find that we don't get flat lines. Ideally, I'd like, if I had an 80 nanometer CD on the mask, I would want to get an 80 nanometer CD on the wafer for every single pitch. But you see, I don't get that. I get a variation. And that variation is a function of the CD. So 100 nanometer CD with 100 nanometer space next to it prints at the right size, but as soon as I change the pitch, I see that the CD first goes down for, say, a 250 nanometer pitch, and then starts rising as the pitch gets bigger. So this is called a CD through pitch curve, and it explains a lot of the proximity effects that we're seeing in lithography. The exact shapes of these curves are very much dependent upon the numerical aperture, the wavelength, the partial coherence, sigma, and this COG acronym I haven't explained yet. It's chrome on glass. It's the type of mask that we're using, which is a standard chrome mask on a glass substrate. When we get to phase shifting masks next time, we'll see that there are other styles of masks besides chrome on glass. So we've got this variation which we don't like. For example, this 100 nanometer feature is varying by more than 15% as a function of pitch. Everything else being ideal. I haven't changed dose, I haven't changed focus, don't have any other errors in the process, and still I'm getting a 15% change in the CD just due to the proximity of other features. We need to correct for this. And this correction is called OPC, optical proximity correction. How do we do that? There's two basic ways of doing that. The first way is called rule-based OPC. What I do is I collect this data, CD through pitch, for example, and I see how the CD is varying as the pitch is changing. From this, I predict how I could fix this by changing the CD on the mask. So, for example, if at a 250 nanometer pitch, I'm 15 nanometers too small on the resist, I might increase the size on the mask by, well, probably not 15, maybe 12 nanometers or some number, which I determine empirically to get the correct CD. How much do I have to change the mask CD so that the CD I get on the wafer is exactly what I want, say 100 nanometers in this case? Once I figure out experimentally how much I need to change the mask so that what gets printed on the wafer is the right thing, I put those numbers in a table, and then I look them up whenever I need them. I look at the CD I'm trying to print and the proximity of its nearest neighbor, and from this table I look up how much I have to change the mask to get the correct result. This rule-based OPC is simple, it's fast, but it's not that accurate because we only collect a little bit of data, but the proximity of other things, there's a huge range of possibilities. I could have as the nearby feature another line of the same width, but I could have another line of a different width. Or I could have a more complicated shape that's close by. And so the number of possibilities grows dramatically, but our ability to collect data to figure out what correction is required is limited. As a result, we can only do so much with rule-based OPC. It's fast, it's accurate, that's what makes it, it's fast and simple, which makes it cheap to employ, but it's not that accurate, and the accuracy is generally not adequate for the smallest feature sizes we like to use today. In fact, rule-based OPC has been inadequate for on the order of a decade now. Instead, we've moved to a new form of OPC called model-based OPC. And on model-based OPC, we use a model that calculates what the images are going to be. We calculate the images and predict what the resist pattern will be for a given mask pattern. Then we adjust the mask pattern iteratively in the model until it can predict that we're getting the proper seeding. Well, we have to calibrate these models, so we still have to collect a bunch of data, just like in rule-based OPC. And the more data we collect, the better we're off in terms of calibrating these models. But once we've calibrated them, they will work for any features, any complex patterns, the proximity of other complex patterns. It can predict all of these things and with greater accuracy than rule-based OPC. However, the accuracy is still not perfect. One of the reasons is to make the models better, more physically accurate, requires more computational power. And remember what we have to do here. We have to calculate or predict or model an entire chip. We have to apply OPC everywhere on the chip. Chips have billions of features, and these models, to make them more complex and more accurate, they get slower. And the result is great difficulty from a computation perspective. Today, model-based OPCs run to calculate the correct mask pattern we need, require calculations on hundreds of CPUs, hundreds of computers running in parallel for multiple days in order to make a correction of one mask. Also, these models are empirical in nature, especially when it comes to the photoresist, and therefore they require recalibration every time anything changes in the process. Change something in the process, got to recalibrate your model. And that is also a difficult and time-consuming task. Nonetheless, model-based OPC is the standard for today's chips, and in fact, we can't make chips without model-based OPC today. Let's review what we've learned about OPC so far. Proximity effects are part of the nature of imaging that come about because of the diffraction limitation. And as a result, they vary greatly depending on the NA we use, the wavelength, the illuminator shape, but also they change based on the resist and even how we make the mask. All of these things influence the amount of proximity effects. So anytime one of these things changes, we generally have to think about how it impacts proximity effects and proximity correction as well. The two types of OPC that have been in use, rule-based OPC is simple and fast, but it's not as accurate. We've used them for older generation chips, but once we've reached about 180 nanometer design rules, which was about a decade ago, we have been unable to keep using rule-based OPC, and we've made the switch to model-based OPC. This works pretty well, but requires very complex models and lots of model calibration. It's a very difficult task. A lot of people work hard at building these models and building the software packages to run these models in reasonable amounts of time. Nonetheless, model-based OPC is the standard today. At chip technologies at and below about the 250 nanometer node, you simply have to have OPC. None of our chips would work today without OPC. It's an absolute requirement in terms of making our lithography work at these very small dimensions. So, what have we learned in this lecture? Our first in a set of two on resolution enhancement technologies. First, what are the two types of resolution? What are the three main RET approaches? Resolution enhancement technologies. Why is OPC needed in optical lithography? And finally, what are the two main types of OPC and what are their advantages and disadvantages? Next time we'll talk about the other two approaches to resolution enhancement technology, off-axis illumination and phase shifting masks. Till then.